Awesome. Okay. Well, thank you all so much for coming to the North Houston Space Society meeting. We have monthly meetings, usually the first Saturday of each month, with the exception being in December and July, whenever it's the second Saturday. So it's kind of important to remember for next month. So just want to let you know that this meeting is being recorded and we'll post it on YouTube and on our website, northhoustonspace.org. And just to kind of remind everybody, sort of the purpose of the National Space Society is to promote the vision of people living and working in thriving communities beyond the Earth, of which our guest speaker today, Elliot, actually was an assimilation of what one of those communities might look like. So looking forward to hear about that. Then also the use of the vast resources of space for dramatic betterment of humanity, such as space-based solar power, mining in space, all the insights and things that we'll learn as we venture further into space. So the plan today is basically we'll have some opening remarks and we might have a space communicator speech, which is our program to kind of promote, give people an opportunity to talk about, to practice their communication skills and to share their perspective on space. But actually, there was the potential that the person that was going to give the space communicator speech won't be available at this time. So um, uh, it looks like that uh, you know uh, we won't be doing that. We'll hop directly into space news, and then once we get into the space news, we'll have our guest speaker talk about his experience of growing edible algae on the moon. And then we'll have some Q&A at the end and a chance to share your own personal experiences. And I do have a recording of Brindley giving her final space communicator speech from yesterday. So I'll play that at the end as well. Anyway, with that, Greg, why don't I turn it over to you and let you tell us about the latest happenings in space. Oh, it looks like yep, you might be muted also.
Okay, got that.
Awesome.
Wait a minute. Oh, actually, what are you seeing right now? It's acting differently than normal. I think I'm on the wrong. I have two monitors, and it's a little.
Yeah, we see the other saw the presentation, but it was in the you know with the thumbnails and everything.
There we go. Okay. Okay. Hopefully, you're seeing mostly the screen filled up. Okay.
Yep.
Space news as of November 7th. You notice I finally got a new picture for the front. Got tired of that same moon one over and over again. Talk a little bit more about the lunar news. Is this filling pretty much full screen except maybe for
Oh,
the
it is full screen.
okay, good. Um, we recently, we've talked about the moon, but there's been some new developments, and that's they actually appear to have found some water in the sunlit areas of the moon. It's in the 100 to 400 parts per million range, but it's over fairly large areas of the moon. And this is new. They used to, we always knew we had it in the large shaded craters, but now they're saying there could be little cold traps as small as a centimeter, where there still could be traps of ice. Um, there's speculation. Some people thought, well, maybe there's glass formed when comet material or asteroid material impacts the moon. They're not quite sure about this, but all this is just being determined by spectroscopy. But there'd be about 15,000 square miles that it would apply to. Now it is, pretty low concentration. So the way to summarize that is 12 ounces of water in a cubic meter of the regolith. By comparison, the Sahara Desert would have 100 times that much water. So there's not a lot there, but if we can figure out how to get it, it gives you a good chance of living off the land, more so than we thought anyway. Obviously, it's useful as water, but of course you can break it down by electrolysis and you get oxygen and hydrogen, which you can use the oxygen for breathing, and you can also use rocket fuel. It's interesting how they found it. They found that actually they have this flying infrared observatory called SOFIA. It's this it's this 747 modified here. There they have a big reflector telescope, but various spectrometers and so on, so they can detect things. The problem with detecting water in space is that our atmosphere, pretty much does all the absorbing. So you have to get above that. So it flies up in the stratosphere above most clouds and most water, and so they get a view of it. It may be the only thing of significance ever actually done by this plane in the last 10 years. It's been almost terminated several times. So maybe this will save it, maybe it won't. But anyway, they've made an interesting discovery here. Something else going on with NASA, they have awarded a bunch of these new tipping point contracts. And they've been doing this for something like 5 years, but basically by tipping point, they're talking about a way for the government to accelerate technology and commercialization through public-private partnerships. And the ones they've done this round, they just announced in the last week or so, most of it, 256 million, is focused on in-space refueling or propellant depots, which really means handling cryogenic fluids, that is, liquid oxygen, liquid hydrogen, and methane. It mostly went to United Launch Alliance, SpaceX, Lockheed, and a small company called Aerospace. This is actually a major shift. They really weren't almost even allowed to talk about it because they had the space launch system going on as a large rocket, and you don't actually need the largest rockets to get to places like the moon if you can do more refueling in orbit. You send ships up, you send fuel up, you refuel. So it is actually a rather bold step for them to finally say, okay, we really need to pay for looking into this. There were other issues as well that they spent money on, power in space, precision landing, landing when there's boulder-strewn fields. Right now you look for a big area to land, but this is to handle much more precise movement at the very end, just to avoid landing on a boulder or something, and space communications. A little update on Starlink. We've talked about that before. This is the SpaceX project, providing internet service on a near global basis. And keep in mind that one reason for it is actually to help pay for all the plans for going to Mars. SpaceX, makes most of their money from launch, and actually that market is just too small to support, the kind of plans that Elon Musk really has. So he needed to tap into a much bigger revenue stream, and that's why offering internet service made a lot of sense. So it's a constellation of low Earth orbit satellites, and they're sticking to the plan. Phase one, this 1,440 satellites. They're in 72 orbital planes, and there's a drawing here to kind of show this. Like this red line to be an example of an orbital plane. It's oriented 53 degrees off of the equator. And there's a little diagram down here to remind people about that. Like if you had a satellite going around the equator, it would look like this, kind of horizontally. Tilted at an angle of 53 degrees is what these are. Polar orbit, of course, would be going over the orbits. So anyway, you have 72 of those planes. Each one of those has 20 satellites in it. They're up about 340 miles. The FCC has actually approved 12,000. They have to get involved in the approvals because of the use of the spectrum. And they've applied for another 30,000. So they have ambitions, of course, to really have a lot of satellites. What is the status now? As of October 24th, with their most recent launch, they've launched 895 satellites, which makes them by far the biggest satellite constellation. Actually, they've already deorbited 51 of them for various reasons. Some of them were just tested. A few of them may have had problems, but there's still 844 up there. So that, as I said, by far, they are the biggest, the biggest operator of satellites in space. So somebody put together a simulation, given what satellites are up there, sort of saying, well, okay, where could you be on the planet and be able to see one of these satellites for communication? And one thing that comes into play right away is, well, what angle are you looking? So imagine if you're on the ground, if you could send a signal horizontally, you could reach a satellite pretty far away, just over the horizon. But the problem, of course, is you'd have trees and things in the way. So it's not very practical. So the target that SpaceX has used is 25 degrees minimum. That is, you're pointing up at least 25 degrees off the ground. And that gives you, a view of, various satellites. They really want to move it in the future to get it to within 35 degrees so that you can have more vertical coverage. So this plot that's shown here is at 25 degrees. And the blue area means you do have coverage for some percentage of the time during the day. Red means none. They'll never cover this because they don't have orbits that are going close enough to the north and south poles. The gold stars here, those represent 100% coverage. And you'll notice where it is. It's really kind of along the Canadian-US border, northern areas. And so they are, that's why they're putting their beta test. They just started it up. It's been kind of creeping in, but they've just gone in a big way over the last month. They sent out emails to people in Washington State, Montana, I guess maybe parts of Canada. But basically, and what they promised in their, what they called their better than nothing beta test was speeds between 50 and 150 megabytes per second. They specify the latency, which they have hoped to get down. Latency is just time delays. They are saying you'll have some you will have some interruptions in your connectivity for various reasons. But the interesting thing is what it costs. So you pay $499 and you get the antenna and a router that goes with it for Wi-Fi use. And you pay $100 a month, $99. And as I said, it's offered at the higher latitudes. And they've offered it in some cases to people for free. For instance, the Washington State Emergency Services, those firefighters, they've been using it and they're actually quite happy with it. Of course, they're getting it for free, so they also appreciate that. They do have one problem, and that's related to ground stations. And there's really two different kinds. You know, there's the user terminals. That's what you get as a subscriber. You know, you pay your $500 and then you can hook up to a satellite. But there's also a need for what are called gateway, other ground stations. Their purpose is to tie into the existing communications infrastructure, typically by a fiber optic link, just like cell phone systems tie into fiber optic links. And if you look at this diagram here, this is actually from an old Iridium diagram, so the satellites don't look the same, but the principle is the same. So if suppose you're a user, you're represented by this guy sitting at a desk, and you're communicating with something else. Say you want to log into your Facebook page. Well, the way you do that is there's an uplink and downlink. You know, data goes back and forth between you and the nearest satellite. That satellite in turn communicates with the gateway, and that's what's tied into the public internet. So you just see this as internet service. It just so happened to go up into the air and back. Now, if you had a user somewhere else over on the far left over here, not quite as convenient for them, unless they have a ground station handy. Instead, what will happen is for them to reach that same server, they go up to a satellite. There'd have to be a crosslink to this first satellite down to this gateway and then onto the public internet. And that all works well. Or it should work well. It certainly has worked in the past. I mean, even going back to Iridium days 30 years ago. Originally, Starlink requested 26 locations for these, and I thought that would be enough. The problem they're running into is that they base their crosslinks on laser communications, which can be much, much higher data rates, but it's a lot trickier to get to work, and they haven't gotten it to work yet. So right now they're kind of stuck. You can imagine just kind of crossing off these crosslinks. That says that every user, for them to communicate with the internet, they have to have a satellite within range. And that means basically about 500 miles or so. So anything beyond that, you need crosslinks. So that's a problem from a commercial standpoint. One, it means you have to have a whole lot more ground stations just to make sure that everybody who might want to use your service has a gateway within 500 miles or so. It also rules out coverage in big areas of the sea. As you were imagining before, that you'd have cruise ships and all these people tying in. Well, actually, they can't do that yet. Even some deserts are just too big where there's no infrastructure. Maybe more importantly, there's going to be lots of countries that aren't all that friendly. That maybe they don't want their own citizens or foreigners to have access to unfettered communications, uncensored internet access. Even places like Cuba and certainly China, they're not going to want people to be able to get up there so easily. So if they can prohibit ground stations, they make it pretty hard for people to get a free flow of information. And of course, it also was a lot of military use for the same kind of reasons. So they do have this problem. They will, at some point they will figure all this out and they'll put up more satellites that, have the crosslinks. But the ones that are up there now, I think right now they're not likely to have too much crosslinking going on. As for what they look like, the little terminal is what you buy for your $500. It just basically is this little dish. And I think I don't think it includes this base, the tripod. There's a little tripod base there that actually you have to pay an extra $100 to get that clamps onto things like this. The gateways are bigger, and this was just assumed. This is not 100% known, but it's assumed that there's gateways. It'll have a similar dish inside, just bigger, and that's the cover is just for protection. It would rotate the same way that the small terminals would. Okay, the main topic will be asteroids today. We've in past news we focused on Mars missions. We focused on other areas, the moon. This time we're going to talk about asteroids, and for reasons you'll see. But there's big questions with them. You know, can we mine them, or maybe even the more distant future live among them? How do we prevent some from hitting the Earth? Do you blow them up? Can you alter their courses? Those kind of questions. And then there's the more scientific issues of do they give hints about the origins of the solar system, the planets, or even life? A lot of the asteroids they have found through spectroscopy that they do have building block chemicals, biological ones such as amino acids and that sort of thing. But to really answer those questions, you have to go there. You need samples and maybe samples brought back. So this is just an artist's conception of an asteroid with some mining going on. Okay, there have been missions to land on asteroids and get samples. Actually, there have been quite a few. Well, there have been two major ones. The previous ones were Japanese. Amazingly enough, the first one was launched in 2003 and returned a sample in 2010. It was only 1 milligram, very, very small. And that was to an asteroid called Itokawa. They have numbers like 25, 143, but then you can name them. So the Japanese decided to name their own asteroids and then go and sample the ones that they had named. They did the same thing with the second probe, Ryugu. And these are actual pictures that were taken from them while they were orbiting before they landed. This second one will be returning its sample in December, so we'll probably talk about this briefly next month as well. We start to get results. It was actually fairly ambitious. They had dropped more than one robotic explorer onto the surface of this thing. They also had used explosives and blasted a 60-foot crater. I don't think this is the crater. I think this picture was probably taken before that. But anyway, they did quite a bit of work to get to that. It takes a long time for these missions. So they launched in 2014. They're returning it in 2020. As for the NASA missions coming up, there's a couple of them. One of them is on an asteroid called Bennu, and that's the one that we just touched, and I'll get to that in a minute. And then there's one coming up on Psyche. This one is interesting because it's mostly metal. A lot of the other asteroids have a lot of carbonaceous materials, meaning carbon bearing, just rocky sort of things. This one may have been, a molten core of a former planet. Whatever's left, whatever might have formed and maybe broken up that made the asteroid belt in the first place. This thing contains 1% of all of the mass in the entire asteroid belt. So it's a heavy thing and hence has a lot of interest. We'll get to that. So Bennu, this is the first one we're going. This is the one we just hit. It's about 1/3 of a mile in diameter, a couple 100 million miles away. It does have a 1 in 2,700 chance of hitting the Earth. So, it's one thing you might want to take a look at. And that's why we did it. It's also interesting from a scientific standpoint that, like a lot of, almost all the asteroids, it's kind of a time capsule. Not much has really changed in them since the birth of the solar system. This also is a live picture, actually taken right before impact, apparently. The mission was called OSIRIS-REX. This is definitely a backronym, meaning they made up an acronym, then they fit some words in to make it up. It's about the size of a van, weighed 4,600 pounds. It was launched 4 years ago, September 16. The overall trip it's taken was the 3 billion kilometers. And that includes, in fact, passing by Earth's gravity one more time along the way in 2017 to get a gravity assist. Finally arrived in 2018. It then orbited for 2 years. I don't know why it took them that long to decide on a landing spot, but it turned out it was more rocky than they expected. And so they really wanted to get it right. And they finally decided where to go. So, touchdown. They touched down for 6 seconds. It basically bumped into it slowly, going 0.2 of a mile an hour. And it just did that on October 20th. It turned out the robot arm that actually is what bumped into the asteroid, it sunk in about 19 inches. The surface was very, very soft. People were joking they could have probably just gone all the way through it. They did blast it with some nitrogen. The idea was to stir up particles and collect samples. They collected about 2 pounds, and they reversed the thruster to back away a bit. And other interesting point about all this is this was all done completely autonomously. It's a long way away. You know, they've gotten better and better at doing these kind of things. So they take pictures um, both originally and then even in orbit, and then as they're doing their landing, they compare where they are to what the video shows them, and they can make corrections based on that. So they've gotten much better at truly being robotic probes, and they really have to be. Um, they did have some trouble. I didn't mention this on the slide, but of course most people know this. They did have some trouble that they collected so much material that they couldn't actually close their sample container. They finally managed to get that straightened away. So they barely have about 2 pounds. So that's a heck of a lot more than the 1 milligram that the first Japanese mission brought back. So this mission, wait a minute. Oh, okay. So anyway, it's backed off and now it's sitting in orbit again around Bennu. It will leave orbit there in March 2021. You know, the asteroid and Earth just line up, you know, for a launch window every now and then, like we talked about last month and 2 months ago in the case of Mars. It'll finally make it back to Earth in September of 2023. It'll drop by parachute down to Utah. They already, of course, know some of the results, not the sample, but just from the impact, they know that the material, at least on the outside and maybe quite a ways in, is pretty low density, pretty porous, and it's just a loose collection of rocks. You know, it's held together by gravity pretty loosely. Let's say that the outer layers, at a minimum, would mostly just break up and burn if it did hit the Earth, burn up in the atmosphere. So, but the way to look at that is that it's really a good idea to get these samples out there, because whatever we see on Earth, by the time they made it to Earth, an awful lot of the stuff is already burned off. So we'll get a quite different picture of what these things are really made of. As far as what it looked like, on the left, we have the picture here. The robotic arm is coming down here on the bottom. It's got one big joint there. And this little thing at the end is about the size of the dish, apparently. That is what you see in this next picture when it actually hit. This is that same dish right there. It hits, and it just kind of blew everything away here. You can see all the particles kind of moving out of the way. So that's what that looked like. Okay, another mission coming up hasn't been launched yet, but it will be launched around July 21st, July of 2021. This one is, in fact, a planetary defense test. It may be the first one. Basically, the idea of diverting an asteroid by crashing into it and changing its orbits. So what they have is a craft, artist conception looks like this. It's about 1,100 pounds. It's going to slam into an asteroid. In fact, it's really a moonlet. This is a binary case here, where you have the main asteroid is called Didymos, and then they nickname the smaller thing that's orbiting it as the Didymoon. Their difference in size, 535 feet versus 2560. Anyway, it's going to hit the smaller one, and then what they'll do is they'll watch how the orbits are changed, and that'll give them an idea that, you know, the kind of calculations we do, you know, are correct. So there are several firsts that come in as a result of this. One is just we will be causing a meteor shower. That's the first human-caused meteor shower. It will eject anywhere from 22,000 to 220,000 pounds of debris, mostly in the centimeter size range. Some of that might reach Earth. There's been a little bit of concern about that, but you know, most of it will probably just burn up. Anyway, they'll measure the orbit change. This will happen in September 2022. That's when the interception will occur. So they launch in July 2021. September 2022 is when they hit it. Another interesting mission coming up is called the NEA Scout for Near-Earth Asteroid. And this is really a test of a very small satellite. It's a CubeSat size, about the size of a large shoebox. And that's for mapping the smaller asteroids. And what we're looking at here, this rather fanciful picture, this is the asteroid they'd be looking at. This thing here is a solar sail. That's a little different. You don't see that too often. The blurry looking thing in the center of that is, in fact, the original satellite. There's a blown up part of it here shown on the left-hand side. So this is the CubeSat itself. But again, starts out the size of a shoebox, and I'm sure it's folded out some solar cells and that sort of thing. But it's going to get there by solar sail. It's actually launching as part of the Artemis 1, the first moon launch. That's the Artemis 1 is the launch that just goes around the moon. There's no landing. So that's coming up. Assuming if that all goes on schedule, that'll be next year, 2021. So that's kind of an interesting one. Some other asteroid missions coming up. One of them is called Lucy. And I don't know too much about this one, but it's sort of interesting in that what they're going to do is they're going for the Trojan asteroids. And these are asteroids that are trapped in Jupiter's orbit. Specifically, they're near the Jupiter Lagrange points, L4 and L5. They're about 60 degrees ahead of Jupiter and 60 degrees behind Jupiter. Those are stable points, so they can tend to accumulate material, and that's what happened. So they're of interest because the theory goes that, well, they could easily be, somewhat different in character. There's a lot of different kinds of asteroids out there, and you figure, well, these are different. Maybe we'll learn something, looking at them. In some ways, to me, the most interesting mission coming up is the one going to Psyche. That's in 2022. And this is the one I talked about. It's the metal asteroid, mostly the nickel iron core, maybe of an early Earth-like planet. So it's not just a rocky thing. It's mostly metal. And as I said, it's 1% of the mass of the entire asteroid belt. So it's a very heavy thing. It's not even that big size-wise. It's only 140 miles wide. The surface area is about that of Texas. Now, if you just calculate, you make some assumptions on the amount of metal there. At current prices of those metals, they're saying that's worth 10 quintillion. Now that's 10 trillion multiplied by a million. Now, obviously, that number doesn't mean a whole lot because, of course, you'd have to actually get it to Earth and down in the atmosphere if you were trying to use it on Earth, and that would be quite expensive. But still, it kind of gives you an idea that essentially there's just huge resources out there in space. We tend to forget about that. We think of it as being rocky and inert, but all those elements that are in Earth, which we normally think of as where our resources are, you pretty much have them out there in space as well. They may be concentrated differently. Earth has had a lot of biological and geological processes to concentrate things like copper, or calcium carbonate, those kind of things. But fundamentally, the atoms are also out there, and we can start using them. So we may never bring back this metal to Earth, but if we never really get going in settling space, there's plenty of resources out there. We don't have to lift everything off of Earth. It can come from other places. The moon, which still has gravity. The asteroid belt has the big advantage that there's no significant gravity to deal with, so there's not much cost there. So this mission, it'll launch in 2022. It'll fly by it'll fly by Mars, getting our gravity assist in 2023, and finally arrive at Psyche in 2026. Now, since this is known to be a mostly metal moon, they're not trying to land and take samples. They're just going to be circling it and taking a lot of pictures and analyzing it, whatever ways they figured out. So again, this picture, this is just an artist's conception. I don't think this is a real picture, but that is, what it might look like. As far as just visualizing how you get there, launches from Earth, goes around, it crosses the orbit of Mars just behind it, so it gets pulled along and sped up. Works its way around another time, finally arrives at the asteroid, and then circles around the asteroid for a year or so. The end of the mission is then listed as 2027. I'm sorry, so it orbits Psyche for 21 months. So other miscellaneous news that's out there. These are just news items in a way. The space station had a little celebration. It's been inhabited continuously for 2 decades now. It's orbited a whole lot of times, hosted 240 astronauts from 19 countries, and is still actively involved in doing a lot of research projects. I think people are now working harder and harder at the commercialization kinds of things. So they're looking very much at what can you do in microgravity. I mean, that's just the premier place to do this. Of course, now there's talk of other space stations as well doing similar sorts of things. Some other news that's come up. Remember last month we talked about the big excitement. Maybe there's life on Venus because they detected phosphine gas. And phosphine gas shouldn't really exist there in equilibrium. So there was hinting at possible life. But now there's been some new studies coming out, even looking at exactly the same data and saying, well, maybe not. Maybe it was just noise and maybe a flawed data analysis. So there will be obviously contention and controversy over this one for quite a while probably, but at least you can't take it as a given necessarily that there is life sitting up in the atmosphere of Venus. Some other smaller items, Voyager 2. After 43 years, it's been out there. That's a long time. It proves that we can actually make craft that last a long time in space. There had been no communications with it for a while. The main reason for that is there's only one place on Earth where we actually have the equipment to do it, and it had been shut down for repairs. It's down in Australia. And the reason for that is in its last course adjustments, but anyway, its final orbit maneuvers ended up taking it heading kind of south compared to the plane of our of Earth. So it's actually only the southernmost observatories in Earth that could even see it. So that anyway, that facility came back online with some new equipment, and it communicated. It sent out, a signal. There's a 17-hour time delay at this point because the thing is 125 times the distance of the Earth to Sun. And then it responded. So at least they know that the Voyager is still alive and well. The other one is too. Voyager 1 is still alive. Other minor news: 7 nations did join the U.S. in the Artemis Accords. And we talked about those previous months. Basically, agreements on respecting existing landing sites, and that no country can own portions of bodies like the moon, but they can be mined, and those properties can be what you mine and extract can be sold. So it's mostly allies of the U.S. that have signed on to this. Notably missing, of course, are China, India, Russia, France, Germany. So not everybody's blood into this yet. Okay, now we're at that point where we ask people to guess how many launches there have been since the last meeting. And I'll make one comment here is that, remember, it doesn't count ones that are suborbital. So if it's just a test like this New Shepard test from Blue Origin, that didn't count. It was suborbital. It actually had paid research payloads on it. So it was a significant test. They're testing the crew capsule, which can hold 6 persons. They actually pressurized it just like they would do in real launches. And they're also testing precision landing. It was actually part of previous studies that NASA had funded on how to land, not hitting boulders and that sort of thing. So, having said all that, okay, are we done with the polling? People taking their guesses. Looks like we got a lot of people guessing 9 or 10. Okay, I'll call an end to it right here. So now the answer is 11, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, in fact, this list, I had to update this list this morning because the Indians just launched the vehicle. So these are mostly pretty routine kind of things, but I will highlight that finally the very last NASA contracted seat where we're paying Russia to take astronauts up the ISS. This is the last one of those. That just went up on October 14th. So that is truly the end of an era. From now on in, it'll be going up in either SpaceX or Boeing craft. The Russians did make this one interesting. It was, in fact, the fastest trip ever made to the ISS. They did it in 3 hours, which is a lot faster than most of the previous ones. Maybe they just wanted to show off. I'm not sure why. Sort of notable, notice that there's actually 180 of those satellites that make up the Starlink constellation I was just talking about. They just went up in this last month. They're really cranking them out. A lot of these launches had been held up for various reasons, COVID staffing and hurricanes and along Florida and those sort of things. And maybe in one other noticeable one, yeah, I guess that's it. Other than that, I'd say they're pretty routine kind of things. Okay, and this brings us up to our speaker. Now, our speaker, Elliot Roth, he's the founder of a company called Spira. They generate better tasting spirulina as an ingredient for food companies. And now this is a virtual meeting, so I guess we can't get free samples. So sorry about that. He is listed as a do-it-yourself astrobiologist and writer. He has 10 years of experience in synthetic biology. He has participated in this high seas program of NASA, which is the one where you simulate living on the moon. Hence the picture down here. This is in Hawaii, so it's a lot nicer the environment than the moon. And that's why, of course, he has a picture here without a spacesuit. He'd be dead otherwise. But luckily, this is really just Hawaii. He has founded multiple companies and nonprofits and spent 5 years in consulting on product design and business strategy. Earlier on, he was involved. He had a fellowship at the Stanford D School, which I'm not too familiar with that. I think it's a design school associated with Stanford. They had a 1-year entrepreneurs program, and it was considered very prestigious, and he was involved in that. He had gotten originally his biomedical engineering degree from Virginia Commonwealth University. So Elliot's going to talk about growing edible algae on the moon, and I'll turn it over to Elliot. So I'll
It's a
stop share.
great introduction, Greg. Thank you so much. Yeah. Just to put it in context, I will be giving a presentation about some of the experimental work I did at High Seas, a little bit of background on the sort of projects that my company is taking on, and in addition to work in space, some of the things that you can take space-based technology and how you apply it to Earth. But seeing as we have like a kind of smaller group and everybody's a nerd here, I would love to have this be a little bit more dynamic. So anytime I'm talking, you have a question or anything like that, feel free to jump in, ask the question, and we'll kind of have this be more of a conversation than anything else. But without further ado, here, let me see if I can share my screen. Let's do this. Okay, cool. All right, that's me. Proof that I was actually there. So, yeah, my experience at High Seas, I was lucky enough to be selected as one of the analog astronaut candidates to participate in High Seas. High Seas is kind of a spin-off of the International Moon Base Alliance. They're dedicated to enabling analog missions and kind of simulating what it would be like to live on the moon in a non-lunar environment. So something where it's a lot safer to test something, test out various technologies. And so we have this sort of habitat as a means of providing a test base for different sorts of technologies that would enable life on other planets. And so due to the pandemic, I was able to get an opportunity to go. They had a call for applications. I ended up submitting my CV as well as some of the experiment ideas. And in total, I did a series of 13 different experiments while I was at High Seas. 4 of those being more psychological research, because the point of this sort of extreme environment is to provide a test basis for new kinds of technologies, but it's really to test the squishy bits, the kind of things that you would have otherwise not been able to do, simulating what it's like to have people living in an enclosed space for long periods of time. So I kind of joked to everybody that I live with 6 roommates and 1 bathroom right now. And so it was kind of an upgrade during quarantine, switching to something where I would be quarantining in a habitat with 5 roommates and 2 bathrooms. So this kind of habitat was established, I believe the first mission started in 2013, but analog missions go all the way back. And in fact, there's an analog simulation in Houston called HERA. And I believe Nathan is organizing some sort of trip or something like that to kind of check it out. COVID willing, things like that. So to put this in context, this is about an hour and a half away from civilization. You can kind of see a little road snaking on back there. It's close enough that we're able to get help if we really need it, but far enough away that no one's going to bother us. We don't interact with anybody. And it's completely surrounded by lava fields. And so when we got to Hawaii, we had to immediately quarantine. Here's another proof of me being there. You ended up kind of going to the staging area, which is kind of this ranch where they build all the technology that outfits the habitat. The habitat itself is powered by solar power with a backup generator. You have a 1,000-liter water tank as a means of supplying the water that's needed for the mission itself for 2 weeks. Then you have it be, it's almost completely enclosed. And anytime you go outside, you have to wear a spacesuit. So this is pictures before we actually entered into the habitat. As you can see, I'm probably like properly showered and everything like that. And so over the course of 2 weeks, you only have what resources you bring with you. And that's part of the point of the extreme environment. So we quarantined in this like little staging area, and then once we arrived from the airport, and then ended up taking the hour-and-a-half drive to the habitat up this winding road up Mauna Loa, which is kind of the second highest mountain on the Big Island in Hawaii. And so, yeah, it was a wild experience. The habitat itself is about 35 feet in diameter. It has 2 floors. It's a little over 1,200 square feet, I think, in total, and then with an attached shipping container. And so you can see here, right about here is the airlock. And so you enter in through this airlock. That's the only entrance into the habitat. And then you have to wait for decompression and everything like that. So you wait 3 minutes. In fact, one of the things that we ended up doing was installing an airlock system while we were there. And then you're able to enter this area over here is the engineering bay on this side. And then the overall habitat floor is kind of right here. The entire habitat is also set up as kind of like a temporary structure. It's something that was assembled on top of a temporary platform and everything like that, just as a means of making sure you don't really don't mar the landscape. It's a national park there, and they have some of the darkest skies in the entire world, which is part of the reason why they have an observatory in Hawaii. And when you're driving on up this dirt road, number one, it's really rocky all the way up there, and you look around and all of a sudden life starts disappearing, and you realize you're going up and up and up and up through lava fields, and all of a sudden you go above the cloud cover. You're about 8,000, 9,000 feet up there, and there's nothing around. It kind of looks like barren asphalt. It's pretty much dead all around, and the only thing that you can see are these lava fields and rocks. So the inside of the habitat was the only place that was really, like, I would say, safe, that harbored life. And so kind of like a bubble, it's a giant geodesic dome. And each of us were given these little workstations to work in. And then we had a small little laboratory there, as well as an engineering bay where we could work on stuff like bioprinting and other kinds of assembly. So we ended up running into some issues in the habitat too that kind of dictated the resource constraints of the mission itself. So you're left with only about 250 gallons of water for 6 people for 2 weeks. And what that really means is that you have to conserve water. So we were granted about 30 seconds of shower time every single day. And surprisingly, not many people actually use that. I mean, I showered once during the entire mission, just doing like a quick bucket shower. And some people never even showered. There were 6 of us there. All of us were practically strangers. We had never really like interacted with each other before we actually arrived. But luckily, the team got along really famously, and we had a really enjoyable experience. So not only did you have water constraints, but we had a composting toilet, two composting toilets, one no flush urinal, and then only freeze-dried food. So we had to bring all of this freeze-dried food with us. So I'll talk a little bit about growing food in this sort of environment and some of the constraints and things that I ended up testing in that kind of situation. Beyond food and beyond sort of the testing of new technologies and things like that, we had air constraints too. So you're in this bubble, and the bubble is almost like completely enclosed. You have one little vent, and our CO2 pump seemed to be on the fritz, and we had consistently elevated levels of CO2. So we would track like CO2 in the habitat, and I'll talk a little bit more about how CO2 constraints played into a lot of my experiments. And then lastly, energy too. So energy is through solar power, but whenever you're on the side of this volcano and you have like a cloudy day or anything like that, oftentimes we had to go into low power mode, and it would get really cold up there because the heaters wouldn't be on and things like that. And so you had to shut down non-essential experiments during those kind of low power days. So we would track things like temperature, water consumption, CO2 measurements, electricity, things of that nature, as a means of really enabling new technologies and trying to figure out, okay, what is the normal situation in which people would live in this sort of lunar habitat? So anytime we went outside, we had to wear these spacesuits. We were covered head to toe in these helmets, gloves, knee pads, air pack. There's these little air tubes that connect to the helmet itself. You put on one of those like Snoopy head coverings. We had little cameras front mounted, and then flashlights. What we were really trying to test with these analog spacesuits was, you know, how does it work and feel with the different gloves, the different setups, and it's supposed to completely simulate you being in a real spacesuit when you're on the moon or on Mars. And so we had these crazy boots and everything like that, and we were tasked by NASA to actually go and investigate lava tubes. And on the side of this volcano, there's lava flows that go underground, and they go deep, deep into the earth. and carve out these massive caverns that we expect are even bigger on Mars and the moon. And in doing so, you can actually build habitats underground to protect against radiation and really kind of enable these, they're almost labyrinth-like living spaces for people. And so we ended up going into these sort of cavernous environments, as you can see right here. This is about, I want to say 20 or 30 feet underground with a little skylight there. We'd climb deep into the earth where there's really very little light in these sort of spaces. And what NASA ended up asking us to do was kind of track what sort of extremophiles or what life forms could be growing in this kind of environment. So this is our mission commander kind of like culturing some of the microbes off of the rock face, kind of collecting samples and seeing really what can live down there, growing on the volcanic rock. And so I had a collaborator sort of, sponsor a specific project. This is a company called Nyoka, and they were kind of producing a bioluminescent glow stick. And so I have this background, deep background in synthetic biology, biotechnology, and this passion in space. And I figured that, lighting systems and things like that, biological in nature means that you can actively replace some of the lighting systems that are more physical in nature, that have potential for breakage or other things like that. So growing your own light underground. And so this is me deep in the caverns of the volcanic mountain, and kind of going about doing a test. You can kind of see we had GoPros and everything like that. And then I had the neck strap with the mounted glow stick. And over here, you can kind of see the kind of illumination. And the camera in the long exposure doesn't really give it credit for what sort of illumination you can get. Think of like fireflies. This uses the same kind of enzyme as fireflies and can provide this really like bright glow in this sort of space. So luckily, I was given this opportunity through my company Spira, and Spira exists to create different forms of like photosynthetic organisms that can replace a lot of the basic fundamental industrial chemicals and ingredients that we use in the supply chain. So stuff like animal proteins or petroleum-based colors. That's really what we're focused on right now. But moving forward into the future, algae in general, which is the category of organisms we focus on, can be used in everything from just basic fundamental production, CO2 capture and absorption, wastewater treatment and management, food production, of course, but also producing the valuable goods that people need in order to survive in this space-based environment. So if you look over here, you can actually see on the left, I was conducting an experiment growing algae on simulated urine. And I was using simulated urine because for safety reasons, we weren't able to use our own urine or anything like that. But I did a number of different tests on growing on simulated lunar regolith, growing on simulated urine, simulated waste, things of that nature, as a means of showcasing that you can produce algae using waste products that humans bring with them. And so this is how algae is normally grown. It's large outdoor ponds. We grow a variety called spirulina that was initially investigated by NASA through their controlled ecological life support system in the 80s. That work continues on now with the European Space Agency's Melissa project, which is really dedicated to trying to figure out how to build a completely closed life support system in which you provide a substantial chunk of the food, wastewater treatment, CO2 capture is provided by algae. And so going from like a large pond system like this and downsizing, how do you actively go about doing that in a way that is effective? And so in these pond systems, we work with farmers all over the world. And we now work with 32 different farms operating in, I think, over 10 countries right now. And in doing so, we produce ingredients at scale for food, cosmetic, textile companies. But the question at hand when I was going about this mission is, how do we actually downsize this into sort of format that would be able to be used in space? And so the solution we really came up with is a little bioreactor setup. It's like a countertop bioreactor and some software that really tracks growth in that sort of environment. So you take the organism, you put it in this growing system, this growing setup, and the idea is that at the press of the button, you can produce pretty much like a meal every single day. And so that would be the ideal in a space-based environment, something where you would be able to produce pretty much your basic nutrition. So spirulina is 60% protein by weight, doubles every single day. It really only requires air, water, light, a couple salts that can be provided through wastewater to grow, and 13 vitamins, 8 minerals. It really is practically everything you need to eat in order to survive. And so in doing so, what we ended up doing was setting up this sort of bioreactor system. And it was a really good thing that I ended up doing. This is my collaborator, Dr. Jessica Snyder. And she's working on another experiment that we ended up doing with mushrooms as a means of growing bricks and mycelium like building blocks, these root structure mushrooms to form the glue to make like building materials. Because our thesis of work, and really the thesis that I was exploring, was how do you provide for people's basic needs in this sort of extreme environment? So this is the little like bucket bioreactor, is really simple. We could really only bring a duffel bag and a backpack on the trip. So I wanted to find something a little bit more compact to grow in. And this is kind of growing using LED illumination, a timer, and everything like that. Just something simple to show the proof of concept work. And I'm really glad that I ended up doing that because as part of our mission, we had to exercise, and this is one of the portholes. There were 2 in the entire habitat. You had to exercise every single day for at least 30 minutes. Or you would go out on these 4-hour EVAs and you would come back like drenched in sweat. There was really no way to get water in the spacesuits or anything like that. And they wanted to kind of limit the potential need for going to the bathroom too, because once you're in that spacesuit, you can't really take it off. So we would have to exercise, and every time we exercised, it raised the levels of CO2 above 1,000 ppm. And so in doing so, it became really dangerous in the habitat because you would wake up in the mornings with like CO2 headaches because of the cramped confines and stuffiness. And so how to go about dealing with that? Well, luckily I was growing algae, and this is kind of correlation, not necessarily causation, but it seems like by growing algae, it sucked down CO2 from the local environment and kind of had the CO2 levels drop by 300 ppm over the course of the 2 weeks that I was growing. And so something like that indicates the potential usage of algae to bioremediate an environment, really provide for a biological way of fixing and really fixing CO2 into something more useful. And currently right now on the ISS, they have these CO2 cartridge-based systems that are like lithium carbide, and they have really high duty cycles and they can fail and other things like that. So as a means of finding a biological replacement, it's something where it can gradually go out of cycle, and you can find ways to repair it as opposed to catastrophic failures. So something like that is really intriguing for the development in space. Ooh, sorry about that. Okay, let me get back on the actual. Give me a second. Okay, there you go. And so we are now currently pursuing a project to send something to the International Space Station that actually absorbs CO2 and turns it into usable substances for astronauts to eat or to use to grow additional things. Something really intriguing for future work at Spira. During the course of my time there, I'm a guinea pig. I'm a do-it-yourself kind of guy. And I was tracking a lot of my biometric data. So as you can see here, I was testing a TENS unit. This is an electrical stimulation device. And it's something that causes muscle contraction. And as a biomedical engineer, we use this a lot to treat pain. My idea was that, okay, well, for long duration space missions, what you're going to be doing is actively trying to figure out ways to prevent muscle degradation. And this was triggering and stimulating my muscles as a means of making sure that, especially, I was like showcasing the abdominal region and stuff like that. So stimulating my muscles and causing them to twitch and basically preventing any sort of muscle degradation over time. So that was one of the more biometric things that I ended up tracking. Of course, I was tracking blood glucose measurements, and I would prick my finger before and after every single meal, before and after sleeping. And I kind of stuck my finger at least 60 to 70 times. I really feel for diabetics now as a means of tracking, diet, consumption, things like that. eating only freeze-dried food also tends to kind of cause gastrointestinal problems. And so we had one of the people on the mission testing microbiomes, swabbing samples all over the habitat, which we took different samples of the entire crew throughout the mission itself. And in doing so, the idea is you're trying to track and measure as much of what's happening living in that sort of environment as possible. And so ended up tracking my sleep patterns and sleep habits as well. As you can see over here, I had 3 different methods of tracking my sleep. And then got a chance to actually experiment with some of our algae ingredients. And so this is using an algae extract to actually make blue pancakes. And so we ended up doing a lot of different cooking experiments while we were there. It's very difficult to use freeze-dried ingredients. And so we had a chance of really like pushing the boundary of what that is like, what that entails. Ate a lot of carbs. And so the idea is to produce food in these sort of environments. And luckily I was able to grow enough of my algae that people could try it and eat it at the very end. It's nice having something fresh as opposed to freeze-dried, especially when you're in this kind of habitat for 2 weeks. And they ended up christening me. Oh, well, I self-christened myself Lord of the Slime. They ended up christening me the Algae Whisperer. This is one of our food experiments. I got a chance to play with slime in a variety of different ways too. And so this is the use of slime mold, which has this really interesting ability to do like computation almost. It is able to solve the traveling salesman problem, which is how do you travel in the most efficient way between multiple nodes in a network? And so we ended up running a couple of different experiments with slime mold. Namely, well, one of the questions we had was, can you use slime mold to figure out the most efficient way to route resources between places in a habitat or in like these lunar caves? And so that was one of the experiments that we kind of what started it all. And then what we did was we actually 3D printed Mauna Loa, the volcanic mountain that we were on top of. And the idea was to put little bits of slime mold in the caldera where it would erupt, and then we could use the like travel of the slime mold and see where it went as a means of kind of mapping where lava tubes might be and might end up. And so that was really fun. No validation there yet, no kind of like experimental result, but something that kind of showcases the potential usage of biology in ways more than just like growing food. So that leads me to like building on the moon. And what we ended up doing was, this is me with some lunar regolith, simulated lunar regolith. And we ended up growing mushroom-based materials in this habitat, in this kind of lunar environment. And so ended up taking some of this mycelium, which is the root structure of mushroom. It's kind of like the fibrous roots that spread out in the undergrowth of the forest, and using that to create bricks and material testing coupons. And so in doing so, we were kind of testing the theory of using mycelium as a glue to pull together lunar regolith and agricultural waste and compost as a means of forming really solid structures that could then be used to build habitats, especially underground in those lunar caves. This was another sponsored experiment by a company called Spout. The issue with water is that once you use water in this sort of environment, you had to be really careful of not using too much. We only had 250 gallons for 6 people for 2 weeks. And so, especially when you're exercising in the habitat, the walls start kind of sweating. You have this condensation and humidity that builds up in there. And what this did is it pulled water out of the air and condensed it into drinkable water. And so something like that allows you to reclaim a lot of the moisture that you're losing. Sort of similar to still suits on Dune. It kind of enables you to reuse and reclaim as much of the moisture as possible. I also ended up testing some physical devices. This was an inflatable drone that I called the donut drone, and ended up testing out something that can be blown up and potentially be used to explore places like Venus in the future. The idea is that you want something really compact. How do you actually inflate a structure that can then be used to move around, and then have as minimal pieces of equipment that you need to bring along with you and kind of enable replacement of stuff. So as you can see, there's only a single rotor, a single prop. it makes it so that it's really easy to blow it up and assemble it in no time at all and kind of replace the different components if they go bad. So I really like to thank my team. We did a number of different interesting psychological experiments while I was there. So one of them was measuring the efficacy of the team itself. I thought our team was exceptionally good. We didn't have any conflicts, which was surprising, being in this cramped environment on top of each other for 2 weeks, no privacy really. And so everybody is like high performing individuals. I mean, it's very challenging when you have scientifically inclined people in a space and get into arguments or other things like that. But for some reason, the composition of the team was perfect. We had a really great camaraderie that was built up. And so huge thanks to JJ, Bailey, Jessica, Michaela, and Paul for being a part of all of this. The kind of experiments that we ended up doing psychologically ranged from measuring the efficacy of the team, the self-efficacy, and kind of the relationship between the two of those in conjunction with USC and the Army Research Lab. Journaling daily, which is what I ended up doing in conjunction with a researcher at Stanford. Then there was a couple of other kind of self-tests. One of them was from UMass Amherst, where you were tracking emotions throughout the day and kind of talking about what you got done, what you didn't get done, how you feel about that. And then lastly, measuring, I ended up playing nature sounds in conjunction with the University of Rochester PhD, kind of playing nature sounds at the beginning and the end of the day, and then seeing how that kind of either made you feel more at home or homesick on the basis of that. And so some interesting psychological experiments that can be tested in this environment as a means of understanding how people perform in these sort of spaces. And so if you ever want to test yourself in an extreme environment and see how you get along with people, I highly recommend this sort of work. And so I kind of like the idea of using biology in this space-based environment is to kind of imagine how you might live in space in kind of a way that isn't just making do, but is in fact flourishing and allowing life to really live among the stars. So how do you kind of take the most minimal payloads and then achieve the maximum output through like in situ resource utilization and kind of making do with what you have and allowing life to find a way. And so I'll kind of like showcase one of my favorite more recent experiments that was done. This is the Chang'e lander on the far side of the moon. And they ended up, the Chinese space program ended up landing this lunar lander. And there wasn't much in terms of the actual headlines about this, but they successfully grew cotton seeds on the moon. So that right there, the arrow is pointing at a bit of cotton that was grown on the moon. And something like that is really monumental because it indicates the fact that you can grow the things, the basic necessities that people need to survive in this sort of extreme, harsh environment. And I think that's what potential analog missions like HI-SEAS, like MDRS and some of the other ones all over the world are able to help kind of showcase a window into, and seeing how we can really test technologies and people in these sort of spaces and environments. So in terms of growing things in these sort of spaces, this is a printed biomaterial that was growing chia seeds while we were there. And so we had the good fortune, my collaborator, Dr. Snyder, ended up growing chia seeds in our habitat. And if we had a little bit more time, we would have had enough to actually eat and harvest and kind of have microgreens and something fresh in conjunction to a lot of the freeze-dried foods and sort of MRE style meals that we were eating. So we started going down the route of also bioprinting a number of other materials. And the idea is you can kind of have a modular assembly of these sort of 3D printed structures, something that would enable more complex geometry and putting together a sort of growth system that could be adapted to any sort of space. And the idea is with bioprinting and biomaterials is that you have something that is definitely adaptable and able to be used in this sort of context. Something that isn't prone to drastic failures that you can actively fix and kind of take care of. And it takes care of you. It was really kind of enjoyable to watch things grow and something that interspersed the days a little bit. We would be very, very busy. We would wake up at 7 in the morning and go to bed kind of around midnight. And so the day was really broken up by some of the experiments we were able to do. And the fact that we were kind of taking care of these organisms, I mean, it means that it also comes back around and takes care of you. So this was the other result of the experiment of material testing of mushrooms. And so watching the mushrooms grow and being able to do we're going into material testing right now to kind of test tensile strength and compressibility and other things like that, hysteresis and whatnot of these materials to see how they actually perform by growing on lunar regolith and with agricultural waste. And so it'll be really exciting to see the outcome of these different experiments, especially because we first started them at high seas, and kind of indicates what can be done to actually construct more habitats like that and make it so that once you plant a seed, in essence, for your initial habitat, you can kind of keep it growing using the resources around you. This is another bioprinted assembly sort of thing. Kind of showcases the complex geometry and some of what can be done to form weaves, interwoven fabrics, different sorts of, manifolds, other things like that, as a means of really demonstrating the additive manufacturing ability. And this is using a kind of reclaimed wood pulp. And you could conceivably believe that you sort of harvest keratin from hair, or you harvest, compost and other sorts of waste, and you can extrude it into 3D printed structures similar in nature, something like this. And so another 3D printed variety of that, this was using the same kind of wood pulp to produce our slime mold, and showcasing the slime mold traveling across the surface and really seeking out resources in life wherever it might be. And so I'm gonna leave all of you with the idea that we really do need farmers on the moon. We need farmers on Mars. We want people to test themselves and test their abilities in these sort of extreme environments, kind of seek out opportunities to be able to go into space fully prepared with biology as a means of really testing the ability to produce in space in the way that enables life on other planets. So ad Astra, and I look forward to your questions.
Sounds good. Everybody should be able to unmute themselves, but if you could maybe raise your hand, I can call on you just to kind of keep people from talking over each other.
And Nathan.
Oh, hey, Williams. Okay.
How are you doing? Great content. Thanks so much for the invite. Sorry, in the very beginning, I could not say hello to you because I need to reset my PC, but everything's fine now. The sound is good and wonderful content from Greg, you, and Elliot. And my question from Elliot is, Elliot, how can you synchronize the metrics between the habitat and Mars, for example? You do that per week. The computers collect everything. You have other instruments, maybe satellites, and you can make sure that you have the same oxygen level, nitrogen level, and everything. I got curious about that. It's pretty cool.
Yeah, the kind of simulation that we end up doing. So there's a couple of things that you can simulate in that sort of space. Like, for example, there's a weather station on the outside that kind of indicates the temperature on Mars. And this sort of environment on the outside. Other things like that, like we ended up decompressing the airlock anytime we went outside. So you had to wait in the airlock for 3 minutes or so while it decompressed and recompressed. And then you wear a spacesuit on the outside. So on the inside of the habitat though, communication and the uplink, downlink from mission control, all communication goes through mission control. So it was sort of like a digital fast for about 2 weeks. Because anytime we wanted something from the internet, we had to go through mission control. And we had a slight delay on receiving Wi-Fi and internet. So I think it was about like 1.7 seconds or something like that to simulate being on the moon. And right now there's actually a Martian crew at high seas, and they have a 30-minute delay. And so something like that. One of them recently wrote about her frustration with the lag time and about how she wanted to kind of like throw her laptop. But the idea is you're in this environment because you chose to be there, and you're kind of following along with what it would be like in that sort of space, and you have to adapt to that.
Super. Thanks so much. Wonderful.
Yeah, that communication time is kind of a key point. A lot of people think that it might be possible for us to go to Mars, but I think the point that people may not be realizing is the astronauts in orbit are supported by this whole army of engineer and scientists and technicians that they have real-time communications with that are kind of helping to guide their activities that you lose whenever you start having 30-minute communication times. So I guess how much of the stuff that you grow did you actually end up eating?
So sadly, what ended up happening is that during transit, a lot of my algae ended up dying. And so I was really kind of saddened when I opened up my duffel bag, my suitcase, and realized that I sort of needed to start from scratch. Luckily, all you really need is one cell in order to start growing again. And luckily, I was able to revive the culture over the course of the 2 weeks that I was there, but I was not able to produce as much as I expected. It was really enough to get like a little tiny taste test for everybody in the habitat. But besides that, yeah, I didn't end up growing very much. I would have liked to be there a little bit longer because then it would have meant that I could have a couple of, growth cycles and ended up really producing food for everyone, really protein dense, nutrient rich food.
Awesome, and I see we have Ian. Mycelium, whenever you said that, I was like, I know Ian has a question.
Yep, absolutely. Hey, thanks for joining this week, Elliot. Yeah, I have a couple questions about, growing stuff in outer space. So as far as the 3D printing goes, with reusable resources, I've always been curious, how would we grow stuff on the moon or on Mars? And you mentioned these huge tunnels that are like more than 20 feet in diameter. So we just like be coating the walls of these tunnels with some of this 3D printed material to grow?
Oh, I'm sorry, you cut out a little bit.
I'm sorry about that. With growing stuff on Mars, so it wouldn't necessarily be on the surface of Mars. It would be in these huge tunnels where some of the 3D print helium and other vegetation.
Yeah. So continue, sorry.
And then also, what was the substrate called? You said it was lunar regula?
Yeah. So to your question about like where we're actually going to be growing and like how these habitats end up getting made, there's a couple of different ideas about that. And if I went back to high seas or had the chance of testing in these sort of cave environments, I would actively try to figure out ways to test habitat formation. And so bring some materials and some sort of inflatable structures too. So the prevailing thought right now, one of the foremost ideas is actually inflatable structures, similar in nature to what Bigelow Aerospace ended up doing on the ISS. And so you go down into these caves, you end up clearing any debris or anything like that, testing for structural stability, adding in struts and supports as a means of making sure that moonquakes or whatever ends up happening doesn't actively cause a collapse and catastrophic failure. And then you end up inflating some sort of dome or structure or something like that underneath the ground, particularly because there's excess radiation in that sort of environment. And so you want to be under the surface to protect against radiation. In terms of growing these sort of structures, the idea is to find ways to use materials on site. And so I was using lunar regolith, which is kind of the crushed up rock of moon dust. And this simulated lunar regolith was kind of taken from the Apollo 17 land site. And you could actually get lunar regolith suppliers if you want to test out growing on moon dust yourself. The idea is that the moon came originally from Earth and has a lot of the same composition. So depending on where you go on Earth, you can actively recreate a lot of the sort of environment that is on the moon. And so mostly silica, right? And silica forms glass. And so it's really brittle and durable. And there's a good material composition and mix of trying to find more brittle composition and something that is a little more pliable, bendable, flexible, extrudable, things like that. So that's kind of the balancing act. And what we were really taking a look at is from these mushroom materials, what is the blend of lunar regolith and then compost? And that compost you can either get from human waste or you can get it from agricultural waste. And so we brought some agricultural waste with us. In fact, you can even form rigid structures if you use a different sort of substrate. And so something that could be used as like a tool or a wrench or, washers, bolts, nuts, things like that, could also be grown rather than brought with you. And so that's sort of the exciting bit about biology in space, is that you can produce stuff in situ using these tiny microorganisms or organisms that do it on your behalf.
That's awesome. And I got another question. So as far as you were talking about the microbiome and like the gut health part of this, did you do any experiments to check like, different amounts of bacteria growing in the microbiome and how it was being affected?
Yeah, there was a number of really interesting experiments that I didn't perform, but the other people on the crew ended up doing. And so luckily we had like 4 biologists on the crew, 3 of whom had PhDs. And so I kind of was able to bounce ideas off of them and stuff like that. One of our crewmates, JJ, ended up taking microbiome samples from all over the habitat. And so she took microbiome samples. We had these swab parties. And so we were able to actually take samples from people. I think we had 3 different times, the beginning, middle, and end of our stay in the habitat. And then also surface samples all over the habitat itself to check the microbiome composition and how it changes. It starts off as a really sterile environment because multiple crews end up staying there. And so we clean pretty extensively. And at the very end, it becomes a little bit more homey and start getting used to the funk, especially when people don't shower or clean themselves as much.
Right.
So it was kind of like interesting to see how things changed over time. To your point about communication, Nathan, Paul, one of the members of our crew, was testing a laser communication system. And so there's some interesting, he also was testing an ozone-based laundry system too. And so using ozone as a means of kind of refreshing clothing. We really didn't end up bringing very many changes of clothing with us. And so you need some sort of way to make it so that you don't smell so bad.
Nice.
Oh, Blanca, I think you're muted.
Yes, I have a question. In regards to the algae, can you do it on Earth to fight hunger, for example, to do it in those extreme climates or places that it's cheap to produce and you can, help with that?
Yeah, that's actually how I initially got started. So I was food insecure myself, living in Richmond. I had set up a laboratory in my friend's garage, and I needed to, after having a couple of consulting projects fall through and clients never ended up paying me, I needed a way to feed myself. And so I looked into what NASA was doing to feed astronauts and came across spirulina. And the UN labeled spirulina as the best food for the future in 1974. But the main reason why people aren't currently consuming it is really taste. And when you take a look at the nutritional composition, it's like almost a complete meal in and of itself. And so I thought to myself, if it's good enough for astronauts, it's probably good for me. And I started growing it and eating it. And I would take big scoops of algae out of these aquarium tanks that I was growing in. And that's how I fed myself in the main protein intake for about 2.5 months. And I realized that fresh algae has no taste. And it's only when you process it and break it down that it starts oxidizing and degrading and causing those negative tasting flavor compounds. So I did a lot of work in flavor genetics and using stuff like CRISPR as a means of knocking out bad tasting flavor molecules. That was my initial work. And then we realized if you ended up pulling out the pigment from spirulina and pull out the pigment of most like algae-based organisms, you're left with this protein powder that's pretty much tasteless and can be used in combination for plant-based milk and meat companies and egg replacement, things like that. So that's kind of the thrust of my research right now. And I had the good fortune of working with organizations like the World Food Program, who recently received the Nobel Peace Prize for their work in preventing hunger and conflict associated with hunger. So that helped us identify a lot of these regions around the globe in developing countries where we're able to work actively with farmers on the ground as a means of providing not only a local protein source in arid regions where they don't really have very much land, they don't have a way to grow things, but something that not only provides them with protein, but employment, and sucks down CO2 from the environment and lends itself to transitioning companies to healthier, more sustainable ingredients. So that's kind of the thrust of the work. Is eventually I want us to live in a place where food is a basic human right, where you no longer have to worry about the scarcity of just having your needs met. And we all have the ability to have like a replicator on our countertop where you press it and you say like Earl Grey tea hot, and you're able to get exactly what you need. So great question.
Thank you.
So Elliot, if we wanted to get some practical hands-on experience with growing spirulina and had no previous experience, how would you recommend us, get started?
So, I mean, we sell growing kits on our website. It's something fun to do. It's something that is a little bit more time consuming than expected, especially because it grows so quickly normally. So you kind of have to want to play around with it and do it as a hobby and other things like that. But you can go on our website, spirainc.com, pick up a grow kit if you really want to start producing your own protein source. We started kind of selling those during the pandemic because, I mean, in case of apocalypse, grow algae, you know? And so we have been helping farmers really all over the world get started as well. And from what we've seen, it's been really rewarding. I had some farmers visit us from Guatemala recently who are growing and producing kind of nutritional supplements for children in the highlands of Guatemala. And so stuff like that is kind of the rewarding parts of my job. I love finding ways to overlap the space-based technology with work in developing countries.
Yeah, it's kind of interesting when we look at water recycling and purification, growing food, kind of being able to take care of yourself, medically speaking, without necessarily having direct access to medical professionals. I mean, all these are problems we have here on Earth and we have in space. So the solutions could be the same.
Yeah, that kind of extreme environment and resource constraint, I think, lends really well to this idea of scarcity. And whenever you're in an environment with scarce resources, how do you actually utilize as much as possible for as little as possible? And so the idea of kind of like recycling things, the idea of being really efficient with energy, with water, with food, with things like that, being able to produce everything yourself in a tiny space for no money and no resources is really exciting because it lends itself to a much cleaner, healthier, more sustainable world. So I'm kind of excited to see the future sorts of technology we'll be able to produce at Vera to kind of get in and shift the world towards those more sustainable choices. Cool.
Hi, Elliot. This is Heather. Thank you so much for your conversation. It's been definitely inspirational. I have a question. I'm looking on your website. What is the difference between electric sky and their spirulina?
Yeah. So one of the things my company does is extract the pigment out of the algae. So it's a blue-green algae, a cyanobacteria. And we pull out the pigment and use that to form electric sky, which is just the blue pigment from it. Regular spirulina is the organism, and then electric sky is just the pigment extract. So we have been working on other sorts of colors as well from algae, just different sorts of carbon negative colors. Most of the colors we actually consume, whether it's the clothes we wear, the cosmetics we put on our face, or really the foods we eat, are petrochemical derived. And so when you think of it in a space-based environment, you don't have the ability to really mine for oil up there or bring all these like oil-based compounds. And in addition, like from an Earth-based environment, you want to produce something that's carbon negative. And so that's sort of what we're taking a look at is how do you produce carbon negative alternatives to petrochemical-based colors and animal proteins as well, because that's kind of the byproduct of all that. I hope that answers your question.
It does. No, I appreciate that. Thank you. And I guess another question is, you mentioned initially early on with your exploration, of course, about high levels of CO2. And so how did that affect, if any, the growth rate of your spirulina?
Yeah. I don't know for sure, to be honest. It's very little growth at the very beginning to be able to check anything, partly because I had to like restart the culture after it crashed. But that's the advantage of biology too, rather than having it be like, oh, just give up because it's not working or something like that. No, I could actually like start with just one cell and grow the entire thing again. The CO2 affected us in other kind of ways though. So there's a couple of different studies out that show CO2 actually affects cognition and your ability to perform like complicated mental tasks, your ability to relate to people, it drives like social conflict quite a bit too. So elevated levels of CO2, you could really feel when it was getting stuffy and it physically impacted you. And so when taking a look at our warming environment and warming world, it sort of indicates the fact that we need alternative ways of producing the basic ingredients, basic things that we consume. Because right now, if we're just constantly emitting CO2, it gets really dangerous, not only from like a climate change and environmental perspective, but also from a performing basic functions and abilities perspective. So I would love to do some additional work and research on CO2 capture and absorption. And in fact, we aim to be sending something to the ISS probably like 2021, 2022 to test out some of our emerging technologies in that space.
Yes.
I had a question related to CO2. What kind of concentrations of CO2 were you typically experiencing while you were there? And what was the range?
So the range started at over 1,000 ppm, and I think it topped out at 1190 was the highest that we saw. And then it trended down to an average of about 700. So still relatively high. On good days, it would be at around like 600. Yeah, good days, it would be around 600.
Okay, so that's actually not that bad. The Biosphere 2, they were in there for 2 years and they ranged between 1,000 parts per million and 5,000 parts per million. Winter, summer, the variations because of daylight and so on. Mm-hmm. I mean, it seemed like they were okay with that. The plants were okay with that. They had other problems like not having enough oxygen at times, so there were other issues. But at least there is an experience there of more than 2 years living at very elevated levels of CO2.
Right. Yeah. I think if we had more time, we could probably end up growing more things too. I think plants really enjoy elevated levels of CO2. They're not so healthy or happy for people.
This is a very interesting discussion. But Greg, when do you think that scientists will be more serious?
Okay.
Sorry, go ahead again, Jack.
I think Jack had to go away.
Oh, okay. Any other questions?
Well, I have a question about the CO2. It's not easy just to have some plants to assist with the CO2?
Yeah. It's mostly a matter of like what makes useful, what ends up converting the CO2 into something usable or useful, right? And like, yeah, sure, you can put some succulents there and like have things where you make it more of a green environment. And that actually lends itself somewhat to the psychological benefit of the team. But really what we were trying to figure out was based on the waste produced by people in this sort of environment, what could you grow? What could you make that solved for people's basic needs? And so that's part of the reason to focus on algae, particularly because it produces protein. It's one of the hardest resources to get in terms of food consumption. And then in addition, it is so fast growing, it doubles every single day. And so that really enables you to have this fast refresh and kind of be able to produce even more of what you need in that kind of environment. If we were relying on conventional sort of crops, stuff like corn, wheat, soy, things like that, it would take quite a bit of time to actually get to the point where we could consume it.
One thing, comparing that to Biosphere 2, one thing to keep in mind is that when you're not photosynthesizing, actually plants respire as well. So they're actually consuming O2 and generating CO2. So for instance, there in their experiments, they found that at nighttime they like to run things cooler, so that the plants didn't, they didn't basically give off as much CO2 in the middle of the night. So there are a lot of tricks that people can play, if you're really in a closed environment like that.
Yeah,
I
yeah.
algae as well. I don't know about the algae. They had algae there, but I don't know.
Yeah, it's something where we got to get tighter monitoring systems around biology. I think NASA really seems to distrust the use of biology in a space-based environment. And so it's because from the very beginning, there was a huge reliance on physical systems as a means of supporting life in space. And so physical systems, you have pretty solid predictability on exactly what physical systems are going to do. And without solid monitoring control and really understanding around biological systems, it becomes more varied and difficult, especially to convince someone that, hey, like there's multiple use cases for biology. So like take algae, for example, there's really 4 use cases that we see. So the first, which is what we're talking about right now, is CO2 capture. Didn't talk too much about wastewater treatment, but nitrogen, phosphorus, potassium, things like that, that's excreted by people can be reclaimed and treated using different varieties of algae microorganisms. You have food production as well. And so that's something that I touched on. But beyond that, I mean, if you enclose a sort of space habitat with something growing, what ends up happening is that absorbs excess radiation, provides a protective barrier for people living in these sort of extreme environments. And so those 4 use cases are really what my team is trying to investigate in conjunction with researchers at NASA.
Yeah, it seems pretty clear that for long-range space settlement, we just pretty much have to depend a lot more on biology. And like you say, it started off as being all technical, and at some point we've got to break that, and it's just messy, and people don't know, and they can't predict it. So the systems will be hybrid for a long time. You're going to use mechanical systems where that'll work, and you're going to use biology as best you can, and it's messy.
Yeah, you want redundancies and fail-safes built in, because otherwise what ends up happening is like these sort of biological systems have an advantage over physical-based hardware because there's no like quick failure modes, right? So physical systems, they fail very, very quickly. Biological systems, they slowly die. So you can see that in some of the plants that you take care of and whatnot, where you need to consistently go and water them. Same thing is true of biology. You can kind of tell when something's going awry. The issue is fixing it in a way where you understand how to go about fixing it. And so that's sort of the kind of things that we're hoping to get better control over, especially using stuff like synthetic biology, understanding the base genetics and exactly what's going on at the small scale.
Yeah, as soon as you start talking synthetic biology, you start thinking, well, gosh, we're going to get to terraforming and all those kind of things too.
I mean, I'm a Venusian, so I actually think we're kind of going the wrong way when it comes to Mars. And I was vindicated while I was in the habitat because they had the phosphine discovery. And so I went around dancing and like kind of cheering to the irritation of all my crewmates. But yeah, it was really part of the reason why I got into algae in the first place is a CO2 based planet, 95 atmospheres of CO2 on Venus. If you go up into the upper atmosphere about 50 kilometers, it's Earth temperature and pressure normal. And so you look at the aerosolized potential for aerosolized bacteria living in that sort of extreme environment. There's real potential there. There's real potential to be able to grow something in a space like that as a means of gradually changing that system, doing something like synthetic ecology in essence, to make it so that you have induced panspermia. You're sending microbes to different places in the galaxy as a means of, seeding life.
Yeah, exciting times coming up.
So Elliot, you mentioned that we're needing more moon farmers per se, of course, looking at the bio and the life of that nature. I'm just curious, what got you interested in this particular field, and how would you suggest us to be able to help spread that word to our younger generation?
Yeah, good question. I mean, I grew up going to Space Coast over the winters because my dad's side of the family actually came from there. And one of his first jobs was parking cars for space shuttle launches. And growing up in that sort of environment, I mean, he's an optical engineer and worked on a couple of different satellites and things like that as a government contractor. But to me, it really instilled this idea of humanity not really having a backup and kind of being stuck on Earth. And so I used to like get neck problems and eye problems by like craning my head in the sky or like trying to stare down the sun or other things like that. And would launch rockets and be really intrigued by this possibility of enabling life on other planets. And so I think part of where I started getting into biology more often than not is I almost set my chem lab on fire. So I was in high school and I would hang out in the chemistry lab and tinker around with different things. And I was doing reaction of glucose and molten potassium chlorate, which burned a hole through the test tube and into the surface of the chem hood. And I at that time, my chemistry professor kicked me out and said, okay, you got to go hang out in biology because nothing's flammable there. So wound up hanging out in the biology room and really became enamored with this idea of DNA being the coding language of life. And so if you have better control over DNA, you have better control over your pretty much like genetic determinism. And this idea that you can tap into these self-replicating systems like von Neumann machines, you know, this idea that you have these little tiny microbes that like double and replicate and can perform tasks. And so I took a look at some of the global challenges. I kind of noticed how I've just come from a place of privilege and being able to utilize that in some sort of way to help the world. I really noticed there's this stark difference between the resources and access that we have here in the United States and elsewhere in the world. And so being able to not only enable access to tools of scientific discovery and opportunity, but enable access to space, enable access to you know, the sort of basic necessities that we have. And I think biology, above any other scientific discipline, has the ability to do that because we interact with biology on a daily basis by just living and breathing. And so that's sort of some of the things that I take a look at. And a community I really got involved in for a while, I've built 5 labs during the course of my career that are open community access laboratories. And so really enabling these sort of tools of scientific discovery come hand in hand with having access to that kind of education or resources or equipment or other things like that shouldn't really be contained within academic environments. So, I mean, the thing that I would pass along to everyone is there are local laboratories, maker spaces and things like that. Get involved in the local community because that's a really good resource as a means of teaching yourself and being able to start moving towards these sort of technologies and enabling life on other planets. So, I mean, I have if you look me up, I have a guide to DIY bio. And so it'll kind of take you through the steps and some of the resources on how to set up your own home lab, things like that. So you look online, like Elliot Roth guide to DIY bio or something, you should be able to find something like that. And that kind of showcases the sort of ability, flexibility, adaptability in biology. You don't need a giant rocket to do biology. You just really need what you have around you. So I would say my recommendation and the message to pass along is, you know, start investigating the world around you, support local spaces that really enable those sort of tools of scientific inquiry, and try to find overlaps and interesting bits where people aren't focusing, people aren't looking. I once kind of made this analogy to somebody that if you wanted to be the world's best violinist, you would have had to start at 2 years of age. And if you want to be the world's best violinist who breathes fire while riding on a unicycle, you can do that right now. And so try to find these like really interesting creative overlaps where people aren't looking, and you'll create entirely new realms of discovery and investigation.
Thank you.
Very long-winded, I'm sorry.
No, that was great.
Paul, did you have a question?
Yeah, I had to find the unmute. Elliot, I'm one of those kind of people that digest a lot of information, and it might take me a day or 2 or 3 or a week. What would be the best way to communicate with you after this?
Yeah, I'm gonna actually change my name to my email so that you can get in touch. There you go. So that's my email, elliot@spirainc.com.
Okay.
Feel free to reach out anytime. I'm always happy to talk about space. I'm always happy to talk about biology, anything at all, really. Yeah.
I will ask one more question while I'm online that I do have. Is there in existence, either with you or somebody else that you know of, a database that tells different types of algae and the amount of CO2 per hour, per square foot, or something like that, that they could digest or use or reclaim into O2 or whatever?
I wish it was that easy. We've been taking a look through a bunch of different papers as a means of identifying that information. If you look up algae CO2 capture, I'm sure you'll be able to find some papers that relate to that. Although that's an excellent idea and something that we should probably put together.
Okay. Yeah, that needs to happen. I read Scott Kelly's book, and he was talking about how those machines up there were making a lot of noise and always failing and always needing repair and all that kind of stuff. So to me, for space democratization or industrialization, we need to really do something different. So
Definitely.
I think the algae is, at this point in time, I think makes a lot of sense to at least delve into several experiments that way. So, all right,
Cool.
That's it. Thank you.
Can I have a last question? Sorry.
Sure, yeah.
Can you modify like the DNA of some of the microbes or algae in order to produce more oxygen and absorb more CO2?
Yeah, actually, we've been working on a couple of different things behind the scenes, some of which involves other types of algae, and really there's different enzymes that actually absorb CO2. So we have a particular setup using something called carbonic anhydrase. It's a type of enzyme that takes CO2 and converts it into carbonate, which can then be stored and captured. And so that's the system that we'll be attempting to apply for grants and sending up to the ISS. I hope I'm aiming for. And I think, Gary, you had a question? Oh, you're muted. Gary, I think you're muted.
Oh.
I didn't have a question. I was speaking to somebody else. Sorry.
Okay.
Oh,
no worries.
Well, while everybody's thinking of their next question, I'd like to go and take a group picture. So if you wouldn't mind turning on your video camera, I could take a screen capture, and that way people kind of get an idea on what kind of group we have. So I think we'll go ahead and take a picture. Okay, so everybody smile. Oops, let me. Okay, 1, 2, 3. Awesome. Thank you all very much. And also, I had a personal request. I'm doing a project that some of y'all know about, where I'm interviewing a person a day till the end of 2024 to find out what people think about our return to the moon. I've interviewed Gary, Elliot is signed up for next month. I've interviewed Kent and Stuart and Ian. So I was looking for somebody to interview today after the meeting, if I could get a volunteer, as I didn't have anybody for today. It's just a brief informal interview. I have a website, countdowntothemoon.org, where I've been publishing them. I have over 300 interviews so far, with 1,500 more to go. Haven't missed a day yet. So, and I think everybody can say that it's fun.
We can communicate after that. I'm gonna send you a message.
Oh, so are you volunteering, Williams, for today? Okay,
yeah.
Cool. Well, I'll interview you then.
Thank you.
Okay, and anybody else have any more questions?
Yeah, Nate, just the last one, build on Blanca and Paul comments. And Elliot, what do you think about the current oxygen cycle for different types of algae? Like in the past, I heard about blue algae versus the other ones that you test. How is it in terms of your experiments, your ideas, and what you intend to do in the future? I don't know if the sound is good.
He may have stepped away for a minute.
Okay, no problem. We're good.
Maybe.
I can repeat the question.
Okay.
No problem. We're good.
Well, I did have one more thing. We do have Brynlee Wright, who's 10 years old. She's given 2 space communicator speeches. She was hoping to attend today, but wasn't able to, but I met up with her yesterday and recorded it. So I'd like to play that for you and get your thoughts. So let me share this out. Hopefully the audio comes through. So let me. Did y'all hear that? So much for giving your third speech. I don't know if that audio came through. Here, I'll play it.
Not getting any audio.
Oh, the audio is not coming through?
No.
That's unfortunate. I don't know how to change that. Well, let's see more. Oh, share computer sound. That would be it. Okay, here we go. Take 2.
Okay.
Well, Brynlee, thank you so much for giving your third speech. Why don't you go ahead and get started?
Hello, my name is Brynlee Wright. I am 10 years old. This is my third speech of the North Houston Space Society Space Communicators Program. My community space speech is on inspiring the Artemis generation. On October 16th, 2020, I went to the Johnson Space Center in Houston for Space Center's Homeschool Day. This was where I was inspired 5 years ago to become an astronaut. There were 2 speakers, Dr. Joy Kelly, the Vice President and General Manager of Jacobs, an engineering company that constructs projects and provides solutions for NASA, and astronaut Brian Duffy, who helped build the International Space Station. What do these people have in common else from working at NASA? Both Kelly and Duffy were inspired by the Apollo mission when they were kids. This is exactly what Artemis, the next mission to the moon, hopes to do with my generation. The name Artemis comes from Greek mythology. Artemis was the goddess of the moon and Apollo's twin sister. The name is fitting because Artemis will send the first woman and the next man to the moon in 2024. The team will visit the moon's south pole, which had never been visited, and according to NASA's website, will search for moon's water and use it for searching the moon to discover its mysteries, learning how to live and work on the surface of another celestial body where astronauts are just 3 days from home, test the technologies we need before sending astronauts on missions to Mars, which can take up to 3 years round trip. Originally, the Artemis generation were just the 13 astronauts who were selected to prepare for the mission. But NASA's administrator, Jim Bridenstine, decided that everyone should be part of Artemis generation to inspire them to continue to explore space. So the term Artemis generation is for everyone, especially people who did not experience the Apollo mission to the moon. To inspire a new generation of astronauts, engineers, and space explorers, NASA's website provides videos and educational activities on their website for parents, students, and educators. The videos are not only on spaceflight, but also on robotics and engineering. They have a section where you can ask an astronaut and some videos from space to connect students with astronauts. And of course, Space Camp remains open, and the Space Center of Houston has expanded their educational programs on the campus for students. NASA has invested a lot on the recent years on the education department, but NASA isn't the only group trying to get young people excited. Different groups have challenges to encourage kids to think about space exploration. One essay I'm working on is on the future of engineers. They had a series of challenges over the years. That current one is Mars essay. And what would you do if you led a team of Mars, led a team to Mars? They also provide many links to learn more about the Mars mission. Former astronaut Leland Melvin actively teaches classes on a day in the life of an astronaut, or how to be an astronaut on an online platform, Varsity Tutors. Local colleges, aerospace programs are providing online and on-campus camps for students to explore STEM. Every day, we are sending more ads online, schools, and coding and robotics. Our 4-H program, which is the largest youth service group in the country, created an activity called Mars Base Camp for the 2020 STEM Challenge. This challenge explored the challenges of getting to Mars, navigating Mars, and landing and growing food on Mars, on the planet. SpaceX recent launches were widely promoted to social media to access people about their next steps to the journey to Mars. As 2024 approaches, we are sure to see much more of popular social media platforms about the upcoming flight to the moon. Social media has provided a way to reach a much wider audience in the entire world. Access to astronauts and current information about space missions have never been more available than it is today. Also, as schools in our country are promoting more and more science, technology, engineering, and math, we are sure to see a generation of young people interested to prepare work in the science field, and for that field to be even more competitive than it already is. The Artemis mission is important because it prepares us to go to Mars, and the Artemis generation is important to inspire a new generation to continue to explore our vast galaxy, to continue to make contributions to our society. Thank you.
Thank you, Brinley. That was wonderful. You've completed all 3 of your speeches, so I'd like to give you a trophy. You're the very first recipient of the Space Communicator trophy.
Yay!
Yay!
Gonna hold it up close and show.
Awesome.
And it says her name. There you go.
Cool. Well, thank you very much. Anyway, she had been here for the past 2 months giving her other 2 speeches, but due to a scheduling issue, she wasn't able to come today. But what did y'all think? Good. Okay. Well, any last questions, observations, anything anybody wants to share? Elliot, I know we had a question right before the video. If you're back, maybe we can ask you.
I can see Elliot's name, but I don't know if he is back yet. Elliot? If not, the worst, I can send a mail to him, and I'm going to copy you, Nathan.
Awesome. Well, I guess that wraps up. Oh, one more question, Paul.
I have recently moved to Houston. It was in the middle of the pandemic, of course, and looked up space groups here, and that's how I found you guys. I've been a member of NSS for a while, but I guess in the midst of the pandemic, nobody's doing any physical meetings right now, or?
Yeah, we were meeting up at Barbara Bush Library up here in the north part of town.
Okay.
They have a room, but since I think April, we've been doing everything online, sort of waiting for the vaccine. You know, the last group of people we want to take out with the pandemic are the space people. So.
Amen. Okay. All right. Thanks.
Nathan?
Yes, Heather?
Hi. I'd love to be able to share your information to those who I work with. I'm currently the executive director of the Science and Engineering Fair of Houston.
Oh, fantastic.
Encompasses 17 categories for both juniors and seniors, 6th through 12th grade. And, I'd love to be able to offer those students this platform so that way they could see experts such as yourselves and garner that information, because they are definitely the pioneers of a generation moving forward, if that's possible.
Oh, absolutely. They're more than welcome to attend our meetings. If they would like to participate in the space communicator programs, that's a possibility, definitely. And then we want to have tours. We went on a tour of NanoRex in January, so they would that would be an opportunity. And we'd like to also do some projects like maybe, I mean, we're kind of open to what they are, but I'm sure the kids have their own ideas, and maybe it's more about just providing support.
Well, absolutely, especially in this pandemic, a lot of the students would go to universities, to their labs to be able to conduct those types of investigations, but now they're confined. And so needing that mentorship is a really vital piece for them. I'm sure that would be very much appreciated.
Yes, what's the best way to get in contact with you?
I guess email you, right? Would that be good? Or
That'd be good, yeah. Nathan.price@gmail.com.
Okay, I'll go ahead and do that. Fantastic.
That's awesome. Well, I guess that concludes our meeting, and we'll just let everybody go. And Williams, I'll keep you around so I could interview you for my countdown to the moon project.
Wonderful, my pleasure. I'll be here.
Thank you all so much. Oh, also next month we're the second weekend in September. I'm sorry, second weekend in December instead of the first one, because the library has their open house the first weekend. So we had already planned on it. Obviously, they're not having their open house now, but still kind of sticking with the original schedule. So, okay, y'all have a good day.
Thank you very much. Have a great day.
Yeah, you too. Thank you.
Have a good rest of the weekend.
Thank you.
Thank you.